Good day, everyone. This is Chris with the Ancient Scholar. So today what I'm going to do is I'm going to start talking about a little bit about organic chemistry. Organic chemistry is at its core the study of carbon and the study of carbon-based chemistry. As we know, carbon is profoundly important for life as we know it. It really acts as a backbone atom. And on this first video, I'd like to talk about what's so special about carbon. Why does it make such a good backbone? So first of all, what I want to do is I'm going to assume that you guys have a fair amount of general chemistry knowledge. I'm not going to really go in review all the general chemistry concepts. I'll assume that we have at least a rudimentary understanding of general chemistry. If you don't, I do have other videos up. You may find this video not very intuitive if you don't have at least a general understanding of, or basic understanding of general chemistry. But let's go ahead and look at the periodic table of elements. So if we look at carbon's here in the P block. It's right here. Has an atomic number of 6. It is in the second period and the fourth group. So it's a period 2 group 4 element. What does that mean? Well, period 2 means that I have 2 shells of energy around carbon. The group 4 refers to the outer shell, known as a valence shell. We know the valence shell is important in chemical bonding. In fact, it's the most important shell when we talk about most of general and organic chemistry. Now, if you are really into inorganic chemistry, specifically the transition metals, you know that things are a little different there. We have energy splitting, and we have things like crystal field and ligand field theories. I'm not really going to cover any of that right now. We're going to stick primarily to the carbon and the P block, S and P block elements, and leave inorganic out of it. Focus on organic at this point. Okay, so carbon is two shells of energy. It is in group 4, which means there are 4 electrons in the valence shell of carbon. And I can go ahead and just draw that carbon, and I'll only draw the valence shell. 1, 2, 3, 4 electrons. So you could look at it like this. That's a valence shell. Of course, we have another shell in there containing 2 the 1s electrons, but we call those the core electrons, and they're really not all that important at this point for chemical bonding. So we won't really even consider them. So carbon would like to have 8 electrons in its valence shell, and 8 electrons in the valence shell is known as the octet rule. And for the most part, atoms are, at least atoms that we'll talk about today, are generally going to be very happy if they can get 8 electrons in their valence, or their outer shell. So carbon needs to acquire 4 electrons to meet its octet rule. So conceivably, carbon can undergo 4 what we call covalent bonds, up to 4 covalent bonds to meet the octet rule. Now, what I want to do is I want to go ahead and talk about the geometry a little bit. The geometry of carbon is very interesting, and we actually have to look at carbon quantum mechanically and use what I will call a quasi-quantum mechanical model, because I'm not going to go into the mathematics of the wave functions and all that, and you know, clearly I'm not adept at doing that anyway, but we can go ahead and look at it qualitatively. What I want to do is I want to just go ahead and do the electron configuration for carbon, and it'll become readily obvious or apparent why we have to look at carbon a little differently. And actually all the atoms a little differently, but carbon in particular. So the electron configuration of carbon, if I start at period 1, that's 1s2. Okay, so my 1s orbital is full, my first shell is full, then I'll move down to the second period, 2s2, okay, and then I'll move down to the third period, not the second period, but my 2s orbital is full, and I'm going to move over to the 2p, and I have 2p, so I have 2 electrons in my 1s, 2 electrons in my 2s, that's 4 electrons. Well, what do I have? I've got 4 electrons, so 2p2, right? The last 2 electrons. That's a total of 6 electrons. So 1s2, 2s2, 2p2. Alright, so What we have here with carbon is we have 2 electrons in the 2s orbital, 2 electrons in the 2p orbital. This is very interesting because I have a total of 4 electrons in the valence shell, but 2 of those electrons are in an s orbital. If you look at the valence shell, so what I'll do is I'll draw the valence shell, and I have the 2s orbital, and then I have all these p orbitals here, and I'll kind of draw them the best I can. So if you can imagine, this would be carbon here. This is a 2s orbital, the black sphere, and then I have my my pz orbital here along the z-axis, my px orbital along the x-axis, and my py orbital along the y-axis. So what do we get here? Well, we get a geometry that's very interesting because I have electrons here in this spherically symmetrical orbital, and then here, these other orbitals, and I kind of get some craziness. And obviously, I have different energy levels, right? In a hydrogen atom, the 2s and 2p orbitals are called degenerate, but this isn't a hydrogen atom. This is a multi-electron atom. So we have some craziness going on, and when we look at the geometry of carbon, it looks kind of like this. I'll try to draw it the best I can. So I have electron probability density here, here, and if you can imagine, these are kind of behind the carbon, and this is kind of coming at you. So it kind of looks like a tripod in a way, where I have these 4 areas of electron probability density kind of coming out, and it's kind of hard to appreciate on here, but all the angles between these different areas of probability density, all the angles are the same. I think it's what is it, about 106.9 or something like that. I'll actually look the actual angles up. And if I'm wrong, I'll correct that in the information box. But be that as it may, that's a very different geometry than we would kind of expect if we just looked at the electron configuration of carbon. So what we do to match what we kind of see in nature is we do something called hybridization. Okay, and what we do is we do some quantum craziness. We take the s orbital. So look, I have the 2s orbital, right? One of those. So I have the one s orbital here. It's in the 2s, but I have one of them, and then I have 3 p orbitals, right? I have the p, x, p, y, p, z, and I have my s. Okay. So I have s, px, py, pz, and what we do is we ask ourselves, will it blend? And we know that really the orbitals are representations of the wave-like behavior, the quantum mechanical behavior of electrons, and we, just like waves, we can constructively and destructively interfere waves. Well, we can constructively interfere these, and what we get is if I take that s orbital, drop it in a blender, take my 3 p orbitals, drop them in a blender, mix it all up, and it has some quantum craziness there. I can actually take linear combinations of these orbitals. What I can get out of it is I will get 4 hybrid orbitals, and we call those hybrid orbitals sp3 hybrids. Okay, sp3 hybrids. So what I'll do is I'll draw the carbon atom, and I've got my p orbitals here, and then I'll show you guys this picture here. Okay, so what I get when I combine these, will it blend? Quantum craziness. I get 4 sp3 orbitals. So I have sp3, 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 and you can see that this matches what we actually see carbon very nicely. That is what's known as molecular orbital theory when I take a lot of hybridized orbitals, okay? So that's actually what we have to do to really understand carbon.